Okay, so good morning, everybody. So I hope you had a nice weekend and refreshed for the next week, like this week. Okay. So this week we have 3 lectures, and so before I introduce the lectures, so I again want to remind you that, okay, I mean, most of you have been attending the lectures, but some of you were missing, and I want to remind you that attendance is a mandatory and it's not optional, because both the lecturers and the organizers and even the institutes put a lot of money, effort to do that. So please make sure that you attend the lectures, okay? I mean, there is a difference, okay, if you have a medical emergency or something, one can understand, but otherwise, yeah, please try to attend the lectures, okay? So today the first talk, we have Professor Deepak Dhar here. I think probably I don't need to introduce him to you. Most of you know him. So I can say that he is probably one of the main figures of statistical physics in India, in the sense that he has trained a large number of students, and that their students have trained gone and trained other students. So the way the statistical physics now in India, he is, I mean, to a large part, he is responsible for it. And he was also so this school has been going on for 15 years. He was one of the lecturers in the first school, and I think again in the 10th school, I think. Okay, so now he's here for the 15th school. Yeah, so I'll not say much, and then I'll just give to Deepak. Yeah, Deepak, please. So he's going to give lectures on percolation theory.
Okay, good morning. You can hear me well? Okay, so there was here. So I would like to discuss percolation theory in these 5 lectures. And so the basic phenomenology of percolation theory is rather obvious. I will try to explain this. So it is at the level of understanding which is very visual and which can be understood by students in the 8th grade or whatever. So what is the problem? The problem is that there is I have some box in which I have spheres of equal size, let us say, but there are 2 different types of spheres. One is metallic and one is insulating. You can take balls of same size made of glass, but one of them is coated by metal and the other is not coated by metal. And then you put them in a box, and then you put above and below some metal sheets and try to measure the conductance of the whole thing, put electric field across and see if current flows or not. And so this is the structure here, and you know the 2 different colors represent the 2 different types of metals, and we would like to know what happens. And it is quite clear that if most of the spheres are wooden or insulating, then there won't be any current, because 1 or 2 metal pieces put in the middle of the insulating sieve will not lead to conduction. On the other hand, if most of them are conducting and a few are insulating, then you will have current going through. Okay? And it's also clear that the current is a increasing function of the metal concentration. So if I take a configuration and change one insulating sphere into a metal sphere, the conductivity can only increase. And so, you know, there must be a transition from non-conducting to conducting state, and there must be only one transition. Once it becomes conducting, then it stays conducting when you keep on adding more metal particles. Metal compared, you know, converting wooden spheres to metal spheres. Okay, so that's the phase transition. So it's clear that the fraction of metal spheres is low, it will not conduct, but if it's high, it will conduct. There is a phase transition from the insulating phase to the metallic phase. Okay, so let us be clear as to what we mean by phase transition here, because this definition of phase transition will be extended to other problems. So usually we have some physical system, and there are some control parameters, you know, like I have benzene liquid and it occurs at some temperature and pressure or whatever. And it has some properties. It has conductivity, it has refractive index and density, specific heat, all kinds of stuff. Whatever you want, you can measure. Then what I do is I change the parameter a little bit. And the properties of the system change with this change in parameters. Okay? And what I do is I'll ask a yes-no question. Because I don't want to ask a very specific, is the specific heat equal to 1.37? Because as soon as I change the parameter, this number will change. But if I ask a yes-no question, okay, then the answer is sometimes yes, and you change the parameter, it remains yes. This question you have to ask somewhat carefully. That depends on the problem we are studying. But right now we are asking, is there a current flowing? And the answer is no, 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 and suddenly it becomes yes. So when the answer changes from no to yes, that is called a phase transition. When it remains one, then it is in one phase. When the answer changes to yes, it's another phase. Okay? In some other problem, I will say that is this looking like a crystal or it's like a liquid, and that will be the phase transition from solid to liquid. So depending on the question, you can ask the definition of the phase, but there is a phase transition. Okay? So it turns out that when we want to study phase transitions, this becomes a very simple model of a phase transition. Everything else is much more complicated than this. So I take it as a prototypical phase transition. It is also called a geometrical phase transition, because all we are dealing with is you have all these particles which touch each other and they conduct or not conduct. That's a geometrical property of sphere packings, if you like, right? And I don't need to know things like temperature and energy and stuff like that, very sophisticated concepts. We will not use them. So we are only going to deal with simple notions of probability and geometry. I cannot get rid of the notion of probability, because this packing which I have made is I just put in spheres and it is a random packing, and next time I do it I will not get exactly the same structure. So we will have a notion of likely configurations, less likely configurations, expectation values. All that stuff will be there. That will be part of statistics, probability. And of course geometry is there to begin with. It is spheres are there and they are touching or not touching, and that's all we will do. But just as an aside, this is a geometrical phase transition. But there are other phase transitions which are also geometrical. It's just for the sake of reference, let me just mention them. So suppose you take hard spheres. We are dealing with hard spheres even here. And I just have a box in which I put these hard spheres and they keep on moving around, kinetic energy. I imagine that argon gas in a box looks like hard spheres colliding. It's a model, but it's a pretty good model. And let us take it as a representative of the real thing. Then, depending on the density of this gas, this substance, sometimes it looks like a gas. At low densities, the spheres can be everywhere. But there is a density beyond which, at high densities, it goes into a crystalline phase. The center of the atoms keep on jiggling, but their average positions describes a periodic lattice. They sit more close to some periodic structure and they deviate from each other, but on the average there is a periodic lattice. Okay? So that is taken to be a model of melting of solids. But for our case, it is just a geometrical phase transition, because all I did was to put hard spheres in a box, and depending on density, there is a phase transition. The question there is it a periodic solid or not? And the answer is no, 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 yes. And so that's a phase transition. Okay. So that's what we were saying, that actually this phase transition shares many common features with other phase transitions and can act as a stepping stone for these studies. So I am sure you have already read some other phase transitions, but I am saying that we don't have to know about them. You can forget about them and you can learn about percolation, And then when you study some other phase transition, you can go back and see that some of the notions you learnt here may be useful there. Okay. So, but I like this quotation from Kesten's book on percolation theory for mathematicians. It is a preface. So, in the preface, the author usually explains why they are writing that book. So, he says that quite apart from the fact that percolation theory has its origins in an honest applied problem, see Hammersley and Welsh, it is a source of fascinating problems of the best kind mathematicians can wish for, problems which are easy to state with a minimum of preparation, but whose solutions are apparently difficult and require new methods. At the same time, many of the problems are of interest to or proposed by statistical physicists and not dreamt up merely to demonstrate ingenuity. Okay, so this is the mathematician's perspective. So the mathematicians are the kind of people who are not interested in applications of their idea. They just think it's a problem, is easy to state, it's nice to study. Okay, so of course there will be some of you who have that motivation and that interest, but you should appreciate that here is a problem which is easy to state, minimum of preparation, and people have been working on percolation problems for over 75 years. And it continues to be a source of interest and fascination. You know, lots of interesting problems come up. You can keep on writing new papers on percolation in general. And so there are a lot of problems of interest, and they are of some use. But just as a counter to this pure mathematical approach to phase problem of percolation, I'm just mentioning that there are a lot of applications. The percolation theory was started out by Hammersley trying to understand gas masks. This was during Second World War, and they were gas masks, and people were interested in making them efficient. And I don't know all this much about gas masks actually, but I know the basic point. The basic point was that there are these carbon particles which can absorb bad gases. So what you do is you make a sheet of these carbon particles and put them on your nose, and so if something bad comes up, then you can use it as a protection for a small time. So that was the thing. But what these people found is that sometimes if you put too little carbon particles, of course it doesn't work or doesn't work well. If you put too much, then it doesn't let gas through. Air cannot pass through, and it becomes impenetrable sheet. And so there is some density beyond which it works, beyond which it doesn't work, below which it works, and you like to be close to that because you want to put as many carbon particles to keep it more effective. So what is that? So that was the problem which Hammersley was asked to study. He was a mathematician, but he was going to work on some war-related effort, and he came up with this picture of the gas masks and percolation. Okay, so unfortunately that is a war-related application, not necessarily my favorite, but let us go on. So Hammersley himself proposed a second application of the general idea. So he said there is a orchard of apple trees, and the trees can be healthy or infected. But if there is an infected tree, it can infect its neighbor. Okay? And then they found that if the trees are close by, then this infection occurs more often. If they are separated, it occurs less often. Okay? So then, when I'm planting trees, I will like to adjust the spacing between trees such that infection doesn't spread too fast. On the other hand, I also want to put as many trees as possible to, keep my profits high. I have to put in effort, and so there is a way to optimize the spacing between trees in the orchard so that it works best. And some ideas of percolation are useful there. What is the idea of percolation? If the infection spreads very far, then it is not good. If it doesn't spread very far, then it is good, right? So that is So sorry, that is the notion of percolation. There are other things, like if you have alloys like or steel, for example. Steel is iron, but it picks up its special properties because you put in a little bit of carbon. Carbon is only a few percent, but you know, because you put in carbon, its properties change a lot, and of course you want to make good steel, then you want to understand how that occurs, and this one is explained by saying that carbon can occur, you know, it doesn't occur on a very regular lattice, it occurs in a random position in the steel form, some kind of a solution. But then if you want to understand the properties of this solution, you got to use the ideas you people have already developed in the percolation theory. Okay? This point I want to make because it's not as if you want to study percolation theory, the only thing I want to do is phase transitions. Because you will never imagine a steel in which there is a phase transition between carbon and steel. Most of it should be steel. And I'm still interested in optimizing the percentage of carbon, not much more than a few percent, and how to do it. You will use percolation theory, but you will not study phase transitions. Okay? There is the oil recovery from porous rock. So, you know, there are these rocks all over the world, but in which there are pores. You know, it is a porous rock, and it's filled with oil at various places. Now, people want to take out the oil from this rock, which is called shale. Okay? So then the way to pull out oil from this rock is to push in steam from one end. So this steam goes in, and oil comes out at the other end, which you can collect. Okay? So that the oil companies do. It's very big business. But they found that when you push steam in, some bit of oil doesn't come out, it remains inside, 20%, which is quite a lot, no? So they want to understand why doesn't it come out, can I make it come out, can I do it better? And the way it is done is to, we will discuss this later. So it was, a model of percolation is used to understand why the oil come out, why does some part of it not come out easily, and what can we do? Okay? So, of course, we have been through very bad times in the recent past. That was this COVID epidemic. And so we already discussed disease propagation in apple orchards. So that is infection processes, whether the infection spreads or doesn't spread. But if you study epidemic spread, in which the agents can move around, they can go to office and infect other people and things like that, then it becomes a different problem. There is a qualitative difference between understanding epidemic spread with moving agents and in apple orchards where the trees don't move. The infection moves from place to place, but the trees don't move. But with people, the people also move and spread the infection, and it is qualitatively different. And of course, it is very important to understand this. So I think several thousand papers must have been written during the COVID period, modeling infection processes and stuff like that. And so, you know, so it has a lot of applications. Okay, just the last one is that all of us use mobile phones. And the mobile phones, of course, are connected to towers, and then through the towers you can connect to everybody else. The given point in a mobile phone is that it should be connected. So, by definition, if it is not connected, it is not mobile phone, it is just some piece of metal in your pocket. So the basic idea of percolation theory, things are connected or not connected, is not working here, because everything is connected as a first requirement. But it turns out that given these things are connected, you can ask how good is the connection, you know, can I, people keep on moving also in cars, so sometimes there are moving agents. So anyway, if you want to study mobile phones, the phone companies will give you some money if you can model it better. And modeling mobile phone networks will be better if you know percolation theory than if you don't, or you will just have to learn. There is a important application of percolation theory to things like mobile phone networks or to social networks. Social networks nowadays are very important because, well, they were always important, but thinking of them as a network has become more important recently. So people say there are all these people, they have connections with other people, and can we understand them, or can we do something about them? I want my brand to spread all over, so can I ensure that it happens, or some such thing. Anyway, there is a lot of application of percolation theory in modeling of social networks. Okay? We will not do it in great detail, but you should be able to think about them and apply whatever ideas we develop here to the problems you are interested in. Okay, so basic models. The model we will discuss is called the site percolation model. There is a lattice, and there is at each site there is a random variable eta, which takes values 1 or 0. It takes 1 with probability Ps and 0 with probability remaining 1 minus Ps. And this occurs independently at each site. This is our basic model. There is a lot of sites, they form a lattice. At each site there is an independent random variable, eta, which takes values 1 and 0. Nothing could be simpler. Okay? So but now comes the, so if I take this problem, which is like an Ising model, there are two variables, and I want to calculate correlation functions of these these variables. They are all trivial. All of them factorize fully. There is nothing to learn there. Okay? So, but even in this trivial problem where all the site variables are uncorrelated, I can define a different quantity which is called the connectivity. So two sites are connected if both of them are occupied and they are nearest neighbors. But if you are connected with somebody who is connected with somebody else, then I am connected with this somebody else as well. Okay, so the connectivity is a relation which is transitive. A is connected to B, B is connected to C, then I say A is also connected to C. So if I take a lattice, there will be some sites with our nearest neighbor connections, and then next neighbor and next neighbor. In the end, there is an equivalence class of all the people who are connected to each other. That is called a cluster. Okay, that's a very simple idea, but that's what we will use. A set of occupied sites connected by nearest neighbor bonds is called a connected cluster. That's our basic definition. And the question we study are statistical properties of connected clusters. Now the problem has become non-trivial because of my definition of connectivity. The site variables are independent, eta are independent at each site, but if I say, is this eta connected to this eta? That's a non-trivial problem. That is what we will study. Okay, so what we defined is called Bernoulli site percolation model, but I can also do similar things with bond percolation. So there will be bonds, so there is a lattice, there are bonds, maybe I should draw a picture. So there are all these bonds present, but some of the bonds are actually, let's say, imagine I erase them. So I erase them independently with probability 1 minus p. They are present with probability p, absent with probability 1 minus p. Again I ask the same question. Can I go from site 1 to site 7? And so that is the question. So this is called the bond percolation problem. You can have more general problem in which both bond and site variables are random, and then if you want to a connection, the site should be present, the bound should be present, then only you can transmit information across. Okay? There is also a notion that a bond percolation problem can be thought of as a site percolation problem, but not vice versa. How does that happen? It's fairly. So here, this is the lattice. I imagine there is a site here. This is a site, 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 this is a site. like that. Okay. Then I assign site variables to these sites. That's the same as assigning bond variables to the original problem. The connectivity is still possible because I say if this site is occupied, this site is occupied, you can go across. So you have to draw bonds. The bonds here will be not the square lattice, they will be like this. Okay, so this is called the matching lattice. So the bond percolation problem becomes site percolation problem on a slightly different lattice. I don't have to work in 2D, I can work in 3D or 4D, and all these problems are defined and they are studied depending on the application. Okay. Okay, so now we come to, so right now all I am doing is I am trying to give a list of the interesting problems we could have studied. It turns out that I have only 5 lectures and I will not be able to study all of them in great detail or explain much about them. But you should just appreciate that we started with this very simple stuff, but it can actually be applied to a large number of cases. Okay, so that we are just discussing this. So here, so I will take a lattice. For convenience of drawing, I just draw the square lattice again. But now I imagine that each bond in this lattice is a resistor. And this is a network of resistors. And these resistors can have different values of resistance. It's a network of resistors. You have studied it in your high school, or at least most of you have studied it in your high school. Okay? So what we are saying here is, now let us imagine that there is a big lattice, 10 by 10 or 100 by 100. Each bond takes, for simplicity, just 2 possible values, R1 and R2. R1 with probability P and R2 with probability 1 minus P. Okay. So what can I say about this network? I told you these are the things, but suppose I ask what is the bulk conductivity of this sample. Suppose I put, all these funny resistors are there, but I put some voltage bus here and here and put a voltage V across it. How much current will flow in this network? Right? That is a non-trivial question, but it turns out that this kind of question becomes quite important because, of course, it's a small lattice, then the answer depends on configuration. If I have this configuration with all of them are 1, then it is one answer. If the 2 is here, then it's a different answer and so on. But if you take a big lattice, then there is a self-averaging involved, and the properties of a big system are independent of the details of the actual configuration. And there is a most likely answer you will get, which is the same. Even if you make another realization, you will get the same answer for things like, so if you calculate bulk conductance, okay, and this is the probability of the bulk conductance. It is very sharply peaked, and this peak becomes sharper if you take a bigger and bigger lattice. So it becomes self-averaging quantity. So in real problems, we are often interested in these kinds of systems which are slightly disordered, but I calculate the bulk property. So it doesn't have to be resistors. I can take some medium, and it has refractive index, glass. But in different parts of the glass, their refractive index is slightly different. 1.3, 1.2, 1.3, 1.2, like that. Now what happens to the bulk system? If the difference in the refractive index is very big, it will become foggy, which I might like, and I want to understand how foggy it is and can I characterize it. But on the other hand, maybe the disorder is small, but there is a bulk value. So if I have an optical fiber, there will still be some variation in the refractive index along the fiber, and I want to calculate the average properties of this system. How to calculate that average? That we will learn at least in some way. Or it is a problem which can be addressed using percolation theory. Okay? So what I called random resistor networks, of course, was a sort of variation of the first problem. We had spheres which were conducting or insulating. And I think the difference is one is a lattice model and one is a continuum model. So we will keep on flipping between lattice models and continuum models. But it turns out that quite often the lattice models are simpler to study, but the qualitative behavior is often similar or same. At my level of thinking, they look the same to me. So we will often study lattice models because they are easier to study. Okay? But I think that is not necessary, and we will do something else if we need to do. Okay, so there is another variation of the same problem, which is called first passage percolation. So this is the same problem as here. There is a lattice, and what I imagine is that there is, this is like this invasion percolation problem I defined earlier. There is some source here of fluid, and I'm pushing the fluid into this medium. Okay? So for the moment, all the bonds are present. The fluid can invade, and so in the end, the fluid will go to the other end. All the sides will be wet, and the fluid will go. But this medium is still porous, and there are pores, and the pores are not of the same size. Some pores are smaller, some are bigger, some are in funny shape. Okay? But they are connected to each other by necks, which are usually smaller than the pore. So when I take a porous medium, I can model it as pores connected by necks. And necks are thinner, and they determine how hard it is to push from one pore to the next. If the neck is very thin, the capillary force is big and you need a high pressure. If the neck is thick, then you can work with lower pressure. Okay? So it becomes easy or hard for the thing to push across. And so if I want to say I want to wet from here to here, how much time it takes for the fluid to reach the next node? That is a time of traversal across a bond. And we will take it to be a random variable, which is not the same at different sites. Okay? And we will say, again, in the spirit of our discussion so far, that all these, each bond has a random variable tau, and we will put an index B for each bond B. Okay? And these tau B are independent random variables. And they are identically distributed, they have the same distribution which I give you. I said this is tau B, and this is probability of tau B, some distribution. Okay? So given this distribution, can I tell how much time the fluid will go from one end to the other? The point is rather simple. If there was just one line like this, then the time to traverse from here to here is just the sum of these random variables, which we know how to study because I know central limit theorem. I have studied it somewhere else. But if there are many parallel paths, okay, then maybe it is easier for the fluid to go like this, and it reaches the end faster. So what the fluid does, it takes all these possible paths and takes the least, lights the path which has the least time. Okay, and so I'm asking that, okay, what is the least time to go from here to there or some such thing. You can ask variations of this question, but what is the distribution of arrival times or some such thing. And so these problems become also of interest. So I take 2 points at distance r from each other, how much time the fluid will take to go from one end to the from one point to the other. Can I study these problems? They have been studied a lot, and they are called first passage because this is the first time the fluid from one point reaches the other point. Okay, so there are many variations of these basic models, sir. But let me mention, I like this one, drilling percolation. So here is a picture. So you take a box, and right now it is taken to be a box with size 4 by 4, no, 6 by 6. And from the top face I look at it, and I drill a hole all the way from top to bottom. But I put this at random, some place or the other I just drill a hole. And then I rotate the box and take some other face and drill a hole and keep on doing it. So the question is, what happens is roughly shown in these figures. In the beginning, it looks very simple. In the end, you have drilled a lot of holes and the stuff is barely connected. And if you drill 2 or 3 more holes, then the thing crumbles into powder. Okay, so the problem is the same. It is at some concentration of holes it was connected, and at some other concentration of holes the different parts of the cube are no longer connected, and so it's a percolation problem. What's the difference? The difference is that the drilling hole is actually a long range connection from one end to the other. So the objects which percolate don't have to be points and bonds. They can be slightly more complicated objects. And of course, this particular paper is some physical review letters in 2016. So you can study such questions and publish them in physical review letters. And it's an interesting question and non-trivial and easy to think about still. So actually, just let me say, theoretically this problem has not been studied much, but you can study generalizations. You can don't drill holes. I can take a 5-dimensional solid and drill 3-dimensional holes, cylinders. Okay, so whatever. These are generalizations of the problem which you can study. Okay, so it says take a large L by L by L cube. Sorry. Take L by L by L cube. On each face, one selects a fraction p of sides and drills a hole perpendicular to face all the way to the opposite face. And so the question is, what is this PC? Turns out that PC is finite. It's around 0.5 for this problem. It's not very small. You might have guessed that if you drill 1%, since they go all the way, it will be very effective. No, it turns out that you need to drill about half the surface will be filled with holes. Can I understand that? Okay, so I will pretend that I am a high school student, and can I understand that as a high school student? You don't need any ideas more sophisticated than what you already know. Sorry? No, in 2 dimensions it doesn't work. You have to work with 3 or more. Okay. Okay, so we have defined the models we study. So what is the basic phenomena which happens? This is easy to understand. We already said it before, but now this is done with more detail with better pictures. So I take this lattice which is drawn here with white and pink colors. And the concentration of these pink dots is varied across this picture. And then if the concentration of pinks is small and the black stuff is the largest connected cluster on this sample. And the largest connected cluster is kind of small, but you increase P, it becomes bigger, and if you increase P more, it becomes even bigger and kind of spans the whole lattice. At still larger values of P, almost everything is connected with a few holes. That's pretty obvious, and that's all that happens. That is the basic phenomenology of the system, is that there is a distribution of cluster sizes, and this distribution, the mean value and whatever the width and so on, they increase as you go close to the percolation threshold. Above the percolation threshold, there is a single cluster which contains a large fraction of all the sites in the lattice, and then there are tiny clusters which are the rest. Everything is not connected, but most of the people are connected to each other in this picture. Okay. So this picture is taken from lecture notes. These references are given so that you can look up these references, and they will perhaps tell more than what I am able to do in these lectures here. Okay. Okay. So this is all it says here. Consider site percolation. That's what we discussed first. Increase PS. The typical size of a cluster increases above a threshold, and above the threshold there is a large cluster containing a finite fraction of the sites. I haven't proved this statement, but we will take it as established by the picture given before. Okay. Finding rigorous proofs of this is an interesting exercise, but left for mathematicians. I am not doing it. Okay, so we can consider several quantities which are usually discussed. One is called the mean cluster size. So you take this big lattice, there is a random configuration, pick a site. I can take it to be the origin, because the problem is all the sites are equivalent as far as at this level of description. We say, what is the size of the cluster which contains the origin? What is the probability that it contains exactly S sites? Okay, and then there is an average value of S, and this average value diverges as P tends to some particular finite value, which is called critical percolation threshold. Yes, sir.
So you have consider the first site percolation. Can you please explain this, what we are considering in this statement? So you have consider first site percolation.
Consider first means I discussed site percolation, bond percolation, and all these correlated site bond percolation, all kinds of stuff.
What do you mean with this percolation word? I don't think.
Percolation. Okay, very good. Percolation is the establishment of a connection. So the usual word we use is, there is this coffee percolator. What is that? There is some medium in which steam is pushed in, and steam goes through these pores of the stuff and comes out at the other end, and with some coffee included. Okay, so it's called, the fluid is percolating in the porous medium. That is the word. It is a colloquial word. It means go through in some random medium. Okay, and so that's what we are doing here, site percolation. Site percolation is percolation problem, which is our particular way we defined it, lattice, and sites are at random variables. We didn't discuss anything called pores in the definition of site percolation. They are just sites, and there is a probability they are occupied and unoccupied. It has been abstracted. The original problem had pores, and we are abstracting it to the problem in which you just have sites present or not present. Okay, so I can look at the mean cluster size, and it increases as a power. So mean cluster size, average in the angular brackets denote average, it's a function of P, and we are taking the limit of large lattices. So then this mean cluster size tends to diverges near PC. Turns out this is a power law divergence. So this diverges as PC minus P to the power something. This is usually called gamma. It's just a symbol, but that's what the convention is to call it gamma. Okay. Then you can also look at things called typical for each cluster. There is the diameter of the cluster, which is the smallest caliper. It's called caliper diameter. You take a caliper and what is the closest you can get without disturbing the stuff and touch it. So it is the maximum of the x1 minus x2, where x1 and x2 both belong to the cluster. You have to do in the x and y direction and take the maximum of both. And so that's the size of the cluster. We have defined a notion of size of the cluster. Each cluster will have a random size. So I can take the average value of psi, which is the mean cluster size. That will also diverge, but it diverges with a different power. It's called nu. Now I'm plotting something else, it behaves differently, but I can actually calculate these functions or determine them numerically from simulation. Okay, and they diverge like these powers. Okay, and then there is this third exponent which is usually defined, is called, so below PC, if you take a point, it belongs to a finite cluster, and the fraction of sites which belong to this cluster is 0 for a large lattice, because the lattice was very big, my cluster was only size 10, then the fractional number of sites which belong to this cluster in the limit of large L becomes 0. But if you go to above PC, then I already said, claimed without proof, is that a finite fraction of all the sites belong to the single cluster. So this is what we will plot. P infinity is the probability that the origin belongs to an infinite cluster, okay, as a function of P, and it does this. At P equal to 1, this probability becomes 1. Below PC, it is 0. And above PC, it's a monotonically increasing function. Okay, this much is easy to see. Then you just say that if you go near PC, how does this change from 0 to non-zero? And it turns out that this goes as a power. So P infinity goes like T minus PC to the power, and that power is called beta. It's just a name. Beta is less than 1. So it goes up like this. Sometimes it is 1. Can I get beta bigger than 1? Okay, if you take funny graphs, it may happen. Okay, so for any given particular problem, I would like to know what are these values of these exponents. And something else I can define just like this, and all those things we would like to understand. So these are the most obvious variables I could define without scratching my head too much, but I can study something else if you want me to. Yes, sir.
In case of mean cluster site, it is mentioned that the cluster containing the origin.
No, so, sorry, just 1 second. Take any cluster. In this case, it was the maximal cluster. But take any cluster, it has a diameter. That is the notion we are defining. For each cluster, there is a notion of diameter. So if the cluster looks like this, I look at the smallest rectangle which will contain the cluster, and the maximum of this and length and breadth is called its diameter. Okay, this is a notion which is very general and simple, and that's what we are using for any cluster. Usually we say containing the origin, because the answer doesn't change if I choose some other site. So but then I would have to use extra notation. I pick a site at random called X and the cluster containing X, and I try to avoid these 2 extra sentences and just say cluster containing the origin. Because the answer is the same, it's independent of X. So why add those 2 extra sentences? Very good. So, right now we have just defined the exponents. It turns out that these exponents do differ from problem to problem, but sometimes they don't differ. So, that is the idea we would like to understand, when do they differ, when they not differ. So, it turns out that if you take some lattice in 2 dimensions, square lattice, hexagonal lattice, triangular lattice, even a random lattice, they usually are the same, they don't differ. But if you change the dimension, then they differ. Okay? But if I can consider other graphs more general, which are not on lattice based, social network graphs. The social network graphs just look like this. There are lots of sites, 1 million of them, and this guy knows these people like that. I cannot draw 1 million sites. But there are 1 million nodes and there are some connected links, and what is the size of the cluster containing this particular site. I can define that. And then I can ask that, what the mean cluster size, what are the exponents. It is still clear that this phenomenology will continue to work, even on social networks. And I will define something called gamma, nu, beta, and what are the values for this, my particular favorite model. So those problems we will, they depend on the detail, and it is nice to figure out what do they depend on and what do they not depend on. Okay. PC is the critical threshold beyond which the infinite cluster first appears. The largest cluster which contains a finite fraction of all the sides. Okay? Yeah, sorry, I was sloppy and I was not defining the limit of large sizes very carefully. But I mentioned it a little bit. I said that if you take small size, then the answers are very sample dependent. But if you take large L, then most of these pictures you will draw will be the same for all clusters, and then the problems we study are in the limit of large L, because they are easier in that limit. Okay, resistor networks. So we already introduced the resistor networks. What are the quantities I can study in resistor networks? So let us consider the simple case where each bond has conductance sigma 1, sigma 2 with probability 1 minus p and p. And sigma 1 is less than sigma 2, just for convention. Okay? So we consider a hypercube of size L and measure the conductance across opposite faces. There is a full stop missing. But define the bulk conductivity sigma in the limit of this conductance. So if you take a large cube of size L, the conductance varies with the size as L to the power d minus 2. In 2D it goes to a constant. In 3D, the conductance is proportional to the area but inversely proportional to the length. So in the end, it's proportional to 1 power of L. In general, D, it's d to the power d minus 2. So you take the conductance and multiply it by L to the power d minus 2. Now this quantity becomes independent of L in the limit of large L, and that is called the conductivity. Okay? So in this case, I have shown this limit L goes to infinity explicitly, but in general, you can, I might skip that detail. And so this conductivity is a bulk property. It is the same for all large samples, and it depends on P and sigma 1, sigma 2, and it is self-averaging. So what can I say about this sigma? That's the question I would like to ask. Okay? Yeah. Okay, very good. So self-averaging means that if you take a big system, it is made up of lots of small parts, and each part has some behavior. But these are random samples, so each part is slightly different from the other, and it is actually, you can sort of say it's an independent realization of the same disorder. Okay? So then when I calculate a quantity which is average over all these subsamples, then you calculate the average answer. And the average answer is the same if you take a different sample altogether. So it is called self-averaging because different parts of the sample average themselves and you get the same answer. It is sort of some version of the central limit theorem. So it says that suppose I take head and tail and I do 1 million heads and tails. Then the fractional number of ones I will get in the end is more or less very sharply peaked at half. Because even though there is a sample to sample variation, the thing is self-averaging, that is the word. It averages itself because different parts of the sample give you the average answer. And
We do not need to average.
sorry?
That means we do not need to average.
Precisely, that is what it means. So an experimentalist, they make some sample and they calculate they take a steel cube and they measure its strength or whatever they want. They don't take 1 million different realization of the stuff and they just take 3 or 5 if they are, very sincere. And the answer is the same. If they took 5 more, it would not differ too much. So that is why we are interested in quantities which are self-averaging so that all different realizations of the same basic issue give me the same answer. So more or less the same answer, that is the point I think. Okay, so what can I say about sigma as a function of p? This is 0, this is 1, this is the range of p. So sigma 1 and sigma 2 are held fixed and I am only varying p. So what can I say about this? Well, I can say that if p is 0, everything is sigma 1, then the mean conductance will be sigma 1. All bonds are the same, so you can calculate the behavior of this network rather easily, I suspect. And so the answer is sigma 1. When all bonds are 2, it is sigma 2. In between, it is some function which is monotonically increasing function of p, and we would like to know what is this function. Can I calculate the whole function? Okay. So turns out that even this simple problem, the answer is not known. Even for a square lattice, if you have these conductances sigma 1, sigma 2, what is this function? Sigma. Nobody knows the exact answer. You can do some simulation, there is an approximate curve. In fact, without doing the simulation, I told you this is how it will behave. So this much we can guess. But can I calculate the exact shape of this curve? That is hard to do. Okay. So people said that, okay, even this problem is pretty hard. Can I simplify it even further? Okay. So one particular simplification which is used quite a lot is to say sigma 1 is 0 and sigma 2 is any number, I can take it to be 1. So you consider the case 0, sigma 1, sigma 2 is equal to 0, 1. So what happens? Then this sigma 1 is 0, then this graph looks like this graph. Up to PC, there will be no conduction. Okay? And beyond that, there will be some, but it turns out that it doesn't increase so fast, it increases somewhat more slowly, like that. I beg your pardon. So in this limit, the graph looks like this. If sigma 1 is not 0, it will look like, it will still go to the same end, like that. So these graphs will vary like this. So what I can say is that what I need is a function which is 0 here but non-zero here. And then when I change sigma 1, this will lift up. How does it lift up? Can I determine this? Can I put any qualitative behavior of this function sigma even if I cannot calculate the whole thing exactly? Okay? So I am saying this to you that you know enough algebra to be able to study this problem on your own. You don't have to look up some other reference, and see what you can determine. Can you say anything non-trivial about this behavior of sigma as a function of p? Can you give an approximate qualitative form of what this dependence can be like? Okay. So the other limit, which is also interesting, is that when this is equal to 1 and infinite. So this network is called insulator conductor network, because the 0 has 0 conductivity, and so the bonds are made up of insulators and conductors, and then the behavior is like this one. There is a second variation of the same problem where the sigma 2 is infinite. So that is called metal superconductor network. Some bonds are superconducting, they have no resistivity. Okay. Then if you go above Pc, then there is a superconducting path from one end to the other, and the resistance of the whole sample becomes 0. But below that, it will be non-zero. So it's the behavior opposite of this. So, well, it's not the opposite, it is similar. It is like this. Sigma is infinite in this whole region, and it is non-zero and finite on the left. Okay? And this function interpolates between both these limits. Okay, so can we determine this function? That is the kind of question we would like to study. Okay. Very good. So in the first case, sigma is 0 for p less than pc. In the second case, bulk conductivity is infinite for p greater than pc. Okay, but there is another property which I can also immediately see without working very hard, which says that this sigma is a function of p sigma 1, sigma 2. But suppose I increase sigma 1 by a factor 2 and sigma 2 also by the same factor. Then the bulk conductivity will increase by the same factor. Right? That is clear to everybody. Right? So I can use this property. So I will write that sigma as a function of p lambda sigma 1 lambda sigma 2 is equal to lambda times sigma p sigma 1 sigma 2. It's a homogeneous scaling function of the variable sigma 1 and sigma 2. Okay? So then I can write this more easily. Sigma is equal to sigma 1 times a function of sigma 2 by sigma 1 and p. What I have done is to get, instead of a function of 3 variables, I am working now with a function of 2 variables. So without working very hard, I have reduced the complexity of the problem a little bit. Okay? So here what people do is that they define an exponent called T1, which is the rate at which sigma increases above Pc in the 0, 1 network. And they define some exponent called T2, which is the rate at which sigma diverges in the 1 infinity problem on the left. And the question is, can you relate at least these exponents the way T1 and T2 diverge? Based on all the things you already know, I mean, nothing new is required to solve this problem. So you can always look up the answer on the internet. It will be there. I think it is there. But you don't have to do it. I'm giving you as an exercise that can you actually determine sigma 2, this T2 if you are given T1. If I know the behavior, this one, can I deduce the behavior of this one? Okay? It is not a very straightforward problem. You need to make some guesses, and that is what I will let you do. Okay? So the problem is well posed, not perfectly well posed, and you have to think about it and come up with the answer. Don't look up on the internet. Come up with the answer by tomorrow. It might be possible to do. You can consult your friends, that's allowed. Okay, very good. I should do it here. Yeah, okay. So for non-zero values of sigma 1 by sigma 2, f is a continuous function of p even at pc. Okay, so this is a tricky point, but actually it is obvious once I write it down. But you may not be able to think of it immediately first time. So I say sigma 1 by sigma 2 is finite. What happens to this function? Does it jump someplace? No, it doesn't jump. It's a smooth continuous function. Even at pc, it will have a finite value. Nothing becomes 0 or infinite. So I'm not going to define critical exponents by whether it becomes 0 or infinite. It remains finite, right? So what can I do? Can I still understand it in some way? And the answer is yes, you must be able to. Yeah, so I don't know, I'm just trying to think about this problem because it intrigues me a little bit. So I take this problem, 0, 1 problem. I'm here. There are a few bonds which are, this is just a near percolation cluster, but there is infinite and it's connected from all sides. Now I increase sigma 1 from 0 to non-zero value. How much will the change occur in the whole network? The conductivity will increase, but by how much? That is what we are asking. Okay? I am asking that can I calculate change in this when I change sigma 1 by a little bit? That might be more tractable than the full problem. Okay. So that problem I'm not discussing more now. That is left as an exercise for you to think about. But I'm doing the same thing with the first passage percolation here. So here also we can study many different distributions of bond traversal times. There is a whole function which, yes sir. Yes.
How did you define T1?
T1 was defined as the rate at which sigma 1 becomes non-zero when p is above pc in the 0, 1 problem. In the 0, 1 problem on this side it was 0, here it was non-zero. But if I let p tend to pc from the right, there is an epsilon which is the difference, then this sigma goes as p epsilon to the power T1. Here it says that sigma is going to diverge as epsilon goes to 0. It will diverge as mod epsilon to the power T2. That's the definition. Okay, so in the first passage percolation also you can study many different distributions of bond traversal times. And we will take again, just simplify the problem. If I understand this T1, T2 problem, then I will understand the rest. So it is in the spirit of my resistor problem where I introduce sigma 1, sigma 2. Here I am introducing T1, T2. And then what happens if you just have values T1, T2? And then again, there is a special case where T1 is 0, T2 is 1. It's like the insulator. This is like the superconductor. So some bonds immediately let you connect and others don't let you connect. So I guess it is, you can look at the time to go from here to here, that is one variable, or you can define something called the velocity of the front, which is inversely proportional to the time. So one of them will become infinite, the other will become 0. I forget which one is which, but it can be done. Okay. So this particular limit T1 equal to 0, T2 equal to 1 is easier to think about. And similarly, you can take T1 equal to 1, T2 equal to infinite. That is like the insulator resistor problem. But now we are dealing with times and not with current flow. Okay. Okay. So there are, depending on P in the first case, this is rather obvious. I already discussed it. That there are one, in this previous problem, T1 equal to 0, T2 equal to 1, there is some region, phase, in which the whole thing just spreads in 0 time. Because there are some paths from which the fluid can go from here to here in 0 time. And there is another region in which it cannot go in 0 time, it has to go through some obstructions. So the time becomes proportional to the length of the sample, and then you can calculate what is this velocity, mean velocity of the front or some such thing. In the second case, sometimes when P is small, then these bonds are very few, then the fluid doesn't go from here to there, it just sticks here. Okay? The mean traversal time to go from here to here is infinite. But in the other case, it can, if these bonds are many, then it will find a path and it will go there, but it will go there with a finite velocity. Okay, so can I determine these functions? That is the kind of questions which people ask. Okay, so the basic result. So in general, you can say I give you a distribution of traversal times, probability distribution of traversal times at one bond, and there are IID random variables. Then what is the velocity of the average front? So the basic result in this case is, I'm just defining the, so the problem is defined like this. I take a lattice, we will take it to be the square lattice again for simplicity. There are all these bonds, all of them have their own independent random variable tau 1, tau 2, tau 3, tau 4 and so on. Then I put a fluid at one point, we will call it the origin, and say how far can the fluid spread in time t, the region invaded by the fluid in time t. Okay, so that will look like this. It doesn't have a very fixed boundary, it is a kind of jagged boundary generally because there is a disorder in the problem. But if I wait longer, then it will invade more. So you get a sequence of these boundaries as a function of t. And we are saying what can we say about this? So the first result, which is very robust, is that the diameter of this invaded region varies linearly with time, asymptotically at large times. Okay, and that is called the velocity of the front. Okay, if I am slightly more careful, I will realize that if I go far, I go proportional to time, the distance traveled. But if I go in this direction, then the velocity is different. So the asymptotic shape of the cluster is not really a circle. Okay, I can see this. Suppose it was just all bonds took 1 unit of time. Then the region invaded by the fluid looks like this. Okay, but if in some other case it will look perhaps more like a circle or not exactly a circle, slightly different shape. It will look like this, which interpolates between a circle and this diamond. So can I determine this function? So this function is called V of omega, where omega is the unit vector which tells me which direction I am going. So in each direction there is a mean velocity of the front, and how much is the mean velocity of the front for a given distribution of bonds variables. Okay. So it says that the exact calculation of V has not been possible for any non-trivial case. See, these problems are easy to define, I have just defined them for you. But if you want to actually calculate, it has not been possible to do this for any f, any non-trivial distribution. And the most studied or the simplest case is the one where the distribution is an exponential distribution. Probability of tau is exponential minus tau by tau 0. But tau 0 I can choose to be whatever, it's just a scale parameter, I can choose it to be 1. So the best studied case is where the problem has a distribution of mean 1. And this is the picture of some such cluster generated by this process, in which the waiting times are exponential with mean 1. So you see, it's an interesting picture, and it has been studied a lot, And this is called the Eden model, and this one has 10 to the power 5 sites. And this reference is 2023, so pretty recent paper. So people keep on studying these problems, not so much progress has been made. I can still publish a paper with this picture, right? So what did this guy do so this problem was called the Eden model because it was defined by a person called Eden. He was studying tumor growth in cancers. Okay, so what happens this is a model again, but let me discuss the model. So it's again something like the apple orchard problem, but it is sort of like this. There is a lattice. This is called the tissue. And in the beginning, all the cells are healthy except there is one tumor cell. And then what happens is that as time develops, a healthy cell neighboring a tumor cell can become mutated and can cause become a tumor cell. So the rate at which a cell, which is a healthy cell but neighboring a tumor cell, becomes infected is called single parameter lambda. Lambda is of course the rate at which this happens, but lambda can be set equal to 1 by resetting the time. Okay, so every healthy cell neighboring a tumor cell gets infected with rate 1. That's the model. Then I just sit here, and after some time, this cell will get infected. But now there are all these perimeters of the original. All of these can get infected. Which one will get infected first? All are equally like, if this one, each one is said to have an alarm clock, which is an exponential alarm clock attached to it. When it goes off, then it becomes infected. So which one will go first? There are 6 clocks. They are all set at start at 0. Then anyone can get infected first. So with probability 1 by 6, any of these 6 neighbors will become infected. Once this becomes infected, then there is a new set of neighbors. And now any of these neighbors will get infected with equal probability. And you keep on doing this, and that is called the Eden model. And do this 10 to the power 5 times, you get a picture like that. And this model, even though it is very sketchy and simplified, but it reproduces the basic phenomenology of the tumor cell growth, which is roughly compact clusters of tumors become bigger and bigger, and they grow with the kind of linear rate for up to a time till the person dies or some such thing, right? Okay. Yeah.
It remains compact for any distribution of times.
Sorry?
It's for exponential distribution.
Yeah, so it turns out that what can happen is that this grows and 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 this grows. In between, this site never, the cell didn't fire. So there might be holes inside these clusters. But if this thing is 10 to the power 5 time steps, this thing has got 10 to the power 5 opportunities to fire. So it will fire at least once. So the inner parts of the cluster eventually get occupied, and the cluster is more or less compact, but it can have holes. In this picture, I think they are not showing the holes, but there are holes near the boundary, but they are usually tiny, and it's interesting to study, the detailed geometry of these clusters or some such thing. We won't do it. Okay, so now I am coming to, there is still 10 minutes, so we can do this. Exact solution of the percolation problem on a line. So you have a line, you have sites, each site is independently occupied with probability P. I take the origin. What is the probability that the origin is not occupied? One of you can answer this one. Anyone? Yes, with some confidence. I have defined the site percolation problem. Every site is independently occupied with probability P, Then I go to the origin and say what is the probability that it is not occupied. I know that several of you know the answer, but one of you should have the courage to speak it out. We are hoping somebody else will do it. Let us see who has the courage of conviction that they can actually say, I know that the answer is this, there is nothing wrong with this. Go ahead. Somebody in the back row, like that one. Can you answer this question? Louder. I can't hear you. Yeah. Very good. So, see, no, all of you, I know that many of you knew the answer, but I'm saying that you should also have the courage and realize that this is a simple question, and in fact 80% or 90% of your audience knows the answer. So then don't be scared of answering it. It helps me if I say some question like this and you say, oh, Q. Okay, very good. Now it is done. What is the so we write it down. Probability that the cluster S has no site, it's called cluster size is 0, is Q. What is the probability that the cluster size is 1? Exactly 1. Now, the site should be occupied, otherwise it doesn't work, but its neighbors should be empty. Otherwise it is not a cluster of size 1. Right? So the answer is PQ squared. It was not very hard to work out. What is the probability that the cluster has size 2?
Why Q square? Because origin may have
Okay, very good. No. So this site should be occupied and this should be empty and this should be empty. Otherwise it is not a cluster of size 1.
we are working in 1D.
So on a line, ऊपर लिखा है 1D. In 1D, the answer is PQ square. I can also do the same thing in 2D, but I am not doing it. Now comes a little bit harder question. What is the probability of S equal to 2? Two sites on the on the occupied cluster. Very good. So no, not so hard. 2p squared q cubed. Q squared. Q cubed. Q squared. No, q squared is good. Yes? Everybody is convinced q squared? I thought it was q cubed. Is it q squared or q cubed? Q squared. Okay, very good. Everybody knows this one. So, I can also write for probability of S is equal to S p to the power S q to the power 2 for arbitrary S. Okay. So then it says SP, that's what is given in equation 1. And then given this distribution, you can calculate the expected size of a cluster, and that is equal to 1 by q. That is some geometric series I cannot sum on the board. Okay, but I can ask more complicated questions. It's not truly complicated, but just the beginning of things to come. So I take this line, I take 2 points, and I say that they are part of the same cluster. I don't care how big is the cluster, but these 2 points should be in the same cluster. What is the probability of that happening? P to the power S. Because this side should be present, sorry, this should be present, this should be present, this should be present, this should be present, so on. So this probability of connection AB, A is connected to B, this is a good notation, okay, is equal to, yes sir, what did you say? Very good, but okay, so we will say the distance is R. R is 1, 2, 3 like that. So what is P to the power? R plus 1. When R is 1, the answer is P squared. No, no, see, it's not a big deal. It's a simple stuff. But I think what we have to do in these kinds of combinatorial problem is to keep track of these simple factors in your head. So you be on the watch out and not make a mistake. When I ask you the answer, you have to say p to the power r plus 1. Okay, very good. So that was the solution to the bond percolation problem is similar. We will not do it here. It's easy. Okay, so now 5 minutes. And in 5 minutes, I want to solve the problem on some other graph other than the line, which was very trivial. It is also trivial, but a little bit less trivial. So that is the point. So we'll take this graph. It is a tree graph with every site has coordination number 3, branching network. And I will just sit at the origin. And I will ask what is the probability the cluster at the origin has size S. Now the graph can be infinite or doesn't have to be infinite. So long as I don't reach the boundary, I'm doing okay. I don't have to take the largest limit to answer this question. So we are coming back to the same thing, and we will ask what is probability s equal to 0 will still be q, s equal to 1 will be p times q cubed now, because there are 3 neighbors which have to be all unoccupied. And when I go to size 2, then there is also something, for each of these ps, I can write a similar formula with a little bit of work that you should do. You should sit down, and when you come here, then you will have to say how many different ways can I form a cluster of size S. Right? You write down make a list and write down the answer. It is a simple answer. It takes 2 minutes. You write it down. And then work for size 3 and 4 and 5. But I want to do it for size 35. To do some big size like that, what I need to do is to use some efficient counting techniques, which is what we are introducing now. So this is called generating function technique. Okay? And I define animal numbers generating function. Animal is a name, so each cluster is called an animal. Why is it called an animal? Because this problem was being studied by a mathematician called Harari. And he took, so Harari was studying the following problem. You have a square lattice, and there is a cluster of S sites which are connected. So how many different shapes of clusters of size 3 can you have? Well, it can be like this, or it can be some rotations of this, or it can be like this. 4 of these and 2 of these, 6 possible shapes. Right? When I take clusters of size 4 and 5, the problem is a little bit more difficult. You have to make a list, right? It can be done. But he was just saying, oh, clusters of size 5 look like this. So he said that this looks like a petri dish on which people, petri dish, people grow cultures, and when they look at the cluster, they see set of spots. And so he said, looks like an animal growing on the petri dish. So he called it an animal. Animal is a collection of cells, and each blob is called a cell. It's actually made up of lots of cells in the real petri dish, but think of it as a blob, and how many blobs are there? That's an animal. So it's called an animal. Once the name has been given, it stucks, and now we don't change it. Otherwise, it just causes confusion. So all these clusters are called animals. So I have just used this terminology. AS is the number of animals of size S. Okay? And here, let us be careful and let us define what is called rooted animals. Okay? So it is animals with a given source, starting point. This point is the starting point, and the animal grows from here. Now, if you give me an animal of size S, I can take any point and call it the root. But then we will think of these as distinct animals with root identified. So if you have animals of size S, there is only one animal of size 1 because the root has to be occupied on my lattice, which is this one. Now, animal of size 2, one more side should be occupied. Any of these 3 can be this one. But so there are 3 animals of size 2 on this lattice. How many animals of size 3? Well, I can have something which is here or here, 6 of them, or I could have it like this, this is the root. 9. That is what is given in the next equation. If I take 2 or 3 more minutes, then this set of slides will be over. So am I allowed? Or there is some lecture immediately afterwards? Okay. So let us stop here. I think it is nearly over, but it's okay. There is no problem because I expect.
You can take 5 minutes.
5 minutes is more than enough. Okay. So, I want to count this generating function. Okay. What is this whole series? If I know the function as a function of x, then I can Taylor expand and get the coefficients. Vice versa, if you know the coefficients, you can sum up a power series and get a of x. Okay. So it's convenient to define a generating function for a cluster. So I have grown up to some stage and I grow further below. Not backwards, but further on. How many ways can I add some bits to a given cluster? So that is called B. And so this is the cluster going with a top side which is fixed, which is the root. So B is similarly counted. It's x plus 2x squared plus 5x cubed and so on. You just count. And this is the equation, which is the main equation. We see that, I don't know. It says we see that A is equal to B, x into 1 plus B times whole cubed. Okay. So it says, I'm counting all possible clusters on this graph. So this will be there. It will have a weight x. If I have a cluster of size s, its weight is x to the power s. I'm summing over everything. Then I sum over everything on this side. So what is that? The answer is, if you sum over all the possible animals on this, it will be 1 plus b. And then if you sum over these, this will be 1 plus b, 1 plus b. You have to multiply all the generating functions to get the full answer. So here, if there are S1 sites, and these are S2, and these are S3, then the weight of this animal in the full thing will be x to the power S1 plus S2 plus S3. So the generating functions multiply. That is what we are using. That is the non-trivial result. And this is the main equation. A is x into 1 plus b whole cubed. But by using the same logic, I get b. I get b is equal to x into 1 plus b whole squared from this picture. This is there, and then this is 1 plus b, and this is 1 plus b whole squared. But this is a quadratic equation in b, and you can solve it explicitly to get this result. So now I have b as an explicit function of x. I can Taylor expand and get all the coefficients. Okay? And okay, I don't know what it is. These exercises I want to do. That we will do later. It says, can you relate the exponents t1 and t2 defined in the random resistor model using some good behavior conditions on the scaling function f? I already mentioned this, but I'm just saying. So here it says, suppose you have a ladder graph like this, and I define the bond percolation problem on this ladder graph. Each bond is independently present with probability p. So can you find the exact correlation lengths? We did the one line problem. This is the 2-line problem. Okay? And This one we will do later because we haven't finished the Bethe lattice calculation. So I will stop here. Okay. Yeah.
So Deepak will be there for the tutorial today at 4:30. So if you have doubts, I mean, you should get them cleared in that, I think. We'll meet at 11:30.
Okay.
This problem on the one which is growing and then how do I the picture you saw 2023 paper. So